talk, which is by Zoe Leinhardt, and she's going to be talking about the story of planets anchoring numerics to reality, which we all need some of. Thank you.
Hello, thank you everybody for coming this morning. And it's a lovely place here in Victoria. Thank you very much for having me. Sorry, there we go. Okay. I will do my best with this mic. Just let me know if all of a sudden you can't hear me. So, today I will start off trying to explain to you, in my opinion as a numericist, how the numerics and theory are sort of playing roles with each other to help us figure out how planets form and why they're so diverse and what the whole story is. So we know that the number of observed planets is increasing every day, and although I have 900 up here, we have 2,000 candidates from Kepler. So we know that we have a huge number of planets, and that they are incredibly diverse. We have, rocky, super-Earth-like planets that are very close to their parent stars. We have hot Jupiters. We have stars that are orbiting planets that are orbiting mature stars. We have planets that are circumbinary. We have planets that are orbiting in a tight binary system, but around one star. Basically, everything that we can think of, we find. And although we may argue about whether or not we have Jupiters frequently occurring around A stars, basically, in my opinion, we have 100% efficiency here. So around any main sequence star that we look at, we should find at least one kind of planet of one flavor. So that is something that numericists and theorists have to make work. And that's our first major constraint, is that planets form very easily, prolific, and whatever we come up with, we must be able to do that. And those planets that we form, they have to have lots of different shapes and sizes and colors and whatever. But it is these observations that are motivating us. Us theorists are scampering behind you observation lists. You come up with these things, these new, beautiful systems that we haven't really thought of. And we're desperately trying to figure out how they form and why there are so many different kinds of systems. But one of the problems with observations is that we only have snapshots. These are not dynamic in most cases. So we have an image of a protoplanetary disk, and then an image of a totally different system that's an evolved planetary system. And somehow we have to get from this point to this point. And for a long time, this whole bit was pretty much a black box. But we are making significant progress now at a pretty quick pace. But a lot of the information that we have, we're not exactly sure what order it falls in. And we don't know if all of these systems go through those intermediate phases. In addition, we need all of these different kinds of science to be going on in order for us to figure out this problem. We need the observations, we need the numerical simulations, we need the theory, and we need the laboratory experiments. None of us are going to be able to do it on our own. Okay, so let me just start with Proplates, because I think they're absolutely fantastically gorgeous. So here we have this beautiful atlas of protoplanetary disks. And this is where we think everything starts, right? The next talk is going to discuss the formation of protoplanetary disks, so I'm not going to talk about it very much. It is definitely not my area of expertise. But you can see here that even these protoplanetary disks are diverse. And they seem to come in different shapes and sizes. They seem to have lots of different dynamics going on. So this is our first stage. And then we come to our pre-transitional and transitional disks. And just as Sean mentioned yesterday, we call these transitional disks because we really don't know what else to call them. They are somewhere in between our full protoplanetary disks and planets. And although we think that some of these have planets in them, we certainly do not know if all of them do. And we don't know what kinds of planets they have in them. We have found a young planet in at least a few. So here we have a lovely transitional disk that has spiral arms, and another one from Japan that also shows another spiral. And then we also have transitional disks that have nice gaps in them. So this is a pre-transitional disk because there's an indication of an inner disk. So this one, even though the gap here is almost 70 AU, it's at 70 AU and it's many tens of AU in size, it still has indication of an inner disk, so it's a pre-transitional disk. And it could be that there is a planet in here, but it is quite hard to get one planet to form such a large gap. So we have to figure out what all of this means. And somehow that fits in between the protoplanetary disk and the evolved system. And all of those disks are just a few million years old. Okay, so then we turn to grain growth, because the idea is that these protoplanetary disks have material that is condensing out and growing, and somehow that solid material makes it into planets. Maybe not always, maybe sometimes you have gravitational instability, but for a lot of our systems, we must have solid material make it into the planets in a dense form. So lots of the observations of these protoplanetary disks indicate that there is grain growth. Some of them, like this guy here, show evidence for very large grains that are non-spherical. And there are lots of other protoplanetary disks in Chameleon and Lupus that seem to suggest that they have millimeter to centimeter sized grains. And there is also protoplanetary disks that don't have a gap in them that show a radial dependence in maximum grain size. So at large semi-major axis, they have smaller grain size, and at smaller semi-major axis, they have larger grain size, which seems to suggest radial drift and growth. Okay, so what happens when we try to do this to figure out what these transitional disks are numerically? So we start off with this kind of a gas disk with an embedded planet in it. And so you can see here there's just a very slight change in surface density. So the gas hasn't been cleared out of the gap formed by the planet. And then if we look at 1 millimeter dust, it's a pretty clean gap. And if you look at 0.1 millimeter, then the gap is much smaller. And this is the process of dust filtration being shown numerically. So you can explain why in some of these objects you would have actually large dust grains make it just to the edge of a large gap, but the small dust grains should go much further in. But in these particular simulations, they didn't clear it up enough to explain the wide gaps in some of these transitional disks. So even in this numerical simulation, they still needed to invoke something like grain growth in order to get rid of the small grains, deplete the small grains enough in the gap to explain observations of these large gap transitional disks. Now this isn't to say that there isn't another explanation for these large gap transitional disks. Okay, so if that's the case and we need to have grain growth, then how do these grains grow? Laboratory experiments suggest that it is possible to grow your grains from small sizes through the centimeter size scale, but it doesn't always work. And it does depend a lot on what those grains and aggregates are made up of. So in some instances, you'd be able to stick two large clumps, two large aggregates together at relatively high velocity, but at lower velocity, those clumps would bounce. And you certainly have problems when you get to larger sizes and you're trying to grow planetesimals. Now, there's going to be a couple of talks on grain growth, I think, and Eugene is going to talk about planetesimal formation, so I'm not going to talk about it for a long time, but I thought that I would give my understanding of the current situation. Okay, so grain growth should theoretically lead to planetesimal formation, though you may also have, right, so grain growth should lead to planetesimal formation. Let's just leave it that way. So planetesimal formation has been sort of the bane of theorists' existence for a long time. It is an incredibly hard problem, and we certainly haven't figured it out. I think that there are lots of ideas, all of which seem to work sometimes and don't work in other situations. And it may be that it's a combination of several of these processes that really gets planetesimals going. Okay, so when I say planetesimals, I mean that you have particles, dust aggregates, that grow up to kilometers in size. So once you get up to kilometers in size, any gas in a smooth disk around a single star would no longer affect those objects. So think asteroids. That's what I'm calling planetesimals. Okay. So we have sort of three main categories of planetesimal formation. One is pairwise accretion, which is a very simple idea. You have two objects, dust bunnies, whatever. They hit each other and accrete and form a larger object. That has had a lot of trouble because it's a very, very slow process. And when you have a turbulent disk, those velocities could get very high. And once you get larger objects, then the smaller objects get sort of kicked around, and it's very easy to get the velocities to be too high for this process to work easily. But there's been some new work this year that suggests that if you take into account the full velocity dispersion, and not the mean velocity. So you include the tail of the velocity dispersion, the slow-moving particles, and you also include non-equal sized impacts. So you have one large guy hitting a small guy, then you can actually get it to work, and you can get significant growth. Gravitational instability, which is just direct collapse of the dust layer, requires an incredibly cold environment, a dense, cold environment. And in general, it's very hard to make this process work without something else to get that dense environment for you, whether that's streaming instability, a pressure bump, or another type of protection mechanism that would consolidate your solid material for you and allow you to reach the criteria needed for gravitational instability. And so that brings us to our sort of third method, which doesn't necessarily which would lead to either gravitational instability or pairwise accretion. So you have sort of dust trapping. So here we have pressure bumps, and you can see the dark lines are solid particles. They're getting sort of gathered in the near edge of the pressure bump. And here are vortices. The red shows you where you have an overdensity of dust material that would either then be able to grow because it's in a low velocity, relative velocity environment, and so the collisions would be low velocity, or you would make it to the gravitational instability criterion. Okay, and so from there, somehow we end up here with planets. And in between, we pretty much can't see anything. We don't have observations of those processes at the moment. And here I'm just showing you some of the most impressive visually direct images of planets. This is by no means supposed to be sort of an example of a proper sort of distribution. So we have this new planet from Subaru, K Andromeda, and Beta Pictoris on either side of its orbit, and of course, HR8799, just to show you a variety of different objects. So it wouldn't be a talk by me if I didn't talk about collisions. So we've come to this point really with not a lot of discussion about the role of collisions. And regardless of how we get to the planetesimal point, collisions are important in forming the planets that we see in most of these systems. In our own solar system, we have evidence of both giant impacts and family-forming events. So giant impacts being the last impact that a planet would have suffered in its evolution, or the last phase of evolution of most of our terrestrial planets. And family-forming collisions result in the dynamical families that we see in the asteroid belt, and theoretically the one dynamical family that we have observed in the Kuiper belt. So we know that in our own solar system, collisions are fundamental. They can also produce observable debris in the early stages of planet formation. And that's also a very interesting thing to consider. But in order to interpret that kind of signal, we have to understand what the collisions do, and we have to have a model to explain that so that we can back out what the underlying population is. Previous collision models weren't created to do that. They were constructed so that you could actually form the planets, not so that you could figure out what the background population was. So in order to do this kind of work, in order to look at sort of young systems and be able to interpret what kind of collisional dust you have and what that means for the underlying planetesimal population, you need to have a new collision model. So that's what I've been working on for the past several years. So before we sort of launch into that, I'd like to go through quickly what kinds of collisions you'd expect to have during during planet formation. So this is the extent of my artistic capability. I apologize. Okay, so we have accretion. Okay, so projectile hits a target and the target gains mass. We have erosion. The projectile hits the target and the target loses mass. Great. But we also have something called hit and run, which is something that Eric Aspog has been working on for a long time with giant impacts. So you could have a projectile bounce off of a target. And that's a pain. The target doesn't change mass, but the projectile may indeed be eroded or disrupted. And then we could also have cratering events, where the projectile hits the target, it's very small, it causes some material to be kicked off of the target, but it ends up in the target, so the amount of mass change is negligible for the target. Okay, so in order to create this new model, what we did was construct a bunch of numerical collision simulations, run them in isolation, and then fit scaling laws to those in order that we would be able to use those results in long-term evolution simulations later, wherever we have collisionally active environment. So we would also expect the velocities during planet formation to vary wildly. So sometimes you would have slow, subsonic, below the sound speed impacts, and sometimes you would have supersonic impacts that went above the sound speed of the material. So here we have a slow impact, but it can still be quite disruptive. And here I'm showing a supersonic impact, where you have a shock initiated by the impact itself, which you can see in gray here. And we then hand off to a gravity code so that we can model the gravitational reaccumulation. And you end up with a remnant, oops. Dave. No problem. So then you end up with a gravitationally reaccumulated object in the end as the largest remnant. Okay. So we did a bunch of these guys, and we also went through the literature and found all of the impact simulations that we could find, and we created a scaling law for the amount of energy required to disrupt our total system. So here we have on the y-axis specific energy, so energy per mass, as a function of combined radius. So if all of the mass of the system, projectile and target, were in one body, with a bulk density of 1 gram per cubic centimeter. So we did lots of densities, lots of different kinds of densities. We even did differentiated objects. But this has all been normalized to 1 gram per cubic centimeter. Thanks. 10. Okay, so you have different colors here, and these are fits to our data at constant velocity. And just to go over the type of simulations that we did, we have rubble pile simulations from 1 to 50 kilometers. Those are the triangles and the crosses. And the color of the actual data indicate the impact velocity. And then we also did some hydrocode simulations of basalt, ice, basalt from Benz and Asphog, and some basalt from Schutze et al. So these all use different codes. They are all some are at subsonic impacts, some are supersonic, producing a shock wave. And yet we are able to come up with an analytic empirical law that fits all of this data. And it's there. Sorry. It actually isn't that bad if you just ignore that strength term. So this whole regime of planetesimals would be in the gravity regime. They're all above a kilometer or so. And that's safely in the gravity regime, meaning that the self-gravity of those objects dominates over its material strength. And that is when this strength term can be dropped. The important bit about this is that it's just an expression. It's just an equation. And we actually have fits for all of the material parameters. And we have a fit for this coupling parameter. So we know, if we were given a specific collision, we know whether or not it's going to result in erosion or accretion. So if it is above this Q star, then your object is going to be eroded. And if it's below it, then it will grow. It is also velocity dependent. So if the impact is fast, it will be harder to disrupt the object in terms of specific energy. And if the impact is slower, it will be easier. Because as you get faster, the energy actually goes into deformation and changing a phase of the material. So a lot of energy is wasted in doing work on that object. When it's slower velocity, you actually just have to move the material out of the way. We also know what the largest remnant size is supposed to be, and we came up with an expression for that, both in low disruption events and when you have a total super catastrophic event. So that means you totally pulverize the system. And so what you end up with in the end is a map of collision outcomes. So on the y-axis, we have the impact speed in units of escape speed. versus impact parameter. Impact angle up at the top and impact parameter at the bottom. And in the green, you see hit and run. Cyan is accretion, and white is erosion for the target. So as you move from left to right, you decrease the mass of the projectile with respect to the target. So here we have an equal mass impact, 1 to 4, 1 to 10, and 1 to 40. And you can see that this line between accretion and hit and run moves over towards the impact in impact parameter. So when you have equal-sized impacts, like the giant impact phase, you're very likely to have hit and run events, bouncing events, where the projectile might be affected, but the target really isn't going to be changed. And as you get a more extreme mass ratio, this is much less likely to occur. And you are either in an accretion space or an erosion space. And just to check this, we looked at some numerical simulations that had been done very carefully to check if their results, not if they were correct, but if the result they predicted fell in the regime that we thought they should fall in based on our model. So Pluto-Charon is a graze and capture impact event, and it fell right on the transition between accretion and hit and run, which is exactly correct. Haumea is a graze and merge event, and it should also fall right on the transition, and it does. We checked a few other high-resolution impact scenarios, and they also fell exactly where you expected them to. So we were very confident with our model predicted outcome map. Okay, so 5 minutes? 3? Okay, 5. Sorry. So we did include this then in a retrospective analysis of planet formation. So we looked at a planet formation simulation that just included perfect merging. And we decided to apply our new model to that because maybe this new collision model really isn't all that important, at least for latter phase planet formation. But of course it is. And it does, when we applied that to our, to the previous numerical simulations, we found that all types of collisions occur. So although the model had assumed only perfect merging, we actually found that about 30% of the time you have hit and run events. You also have partial accretion, erosion, and catastrophic disruption. And so depending on what kind of question you're asking, it may be very important that you include an accurate collision model. We also found that you could change the composition of your protoplanet significantly with one or a few giant impacts. You could end up with an iron-rich object, and you can strip the mantle off of projectiles fairly easily. Okay, so hopefully I've convinced you that collision model, an accurate collision model, is required for understanding the details of the diversity of planets that you would get in the last phase of planet formation. But I certainly haven't discussed why this would be important early, except in the early phase of planet formation, except to sort of allude to the fact that it would be hard to understand what your observations of collisional dust would mean if you didn't have an accurate collision model. So here I just wanted to advertise a poster, 614, that does try and talk about this problem. So we start with a planetesimal disk of 1 million planetesimals with an embedded planet. And there's no gas in this particular set of simulations, just to make the simulation simple. It's not because we think that this is correct. And then all of these planetesimals interact through gravity and collisions, and we predict the dust distribution, the dust surface density, run it through radiative transfer, and come up with a bunch of resolved images. And immediately what you can tell for different eccentricities of planets is that you can see a very significant signature from the collisionally active dust, or the collisionally produced dust. And you can see a difference between a circular planet and an eccentric planet. But these signatures are not unique. They're not unique to collisionally produced dust. We can produce this signature in other ways. So it is non-unique, and we need to work on it more carefully in order to understand what we're actually seeing when we observe these transitional disks. Okay. Oops. No. Okay. So planet formation seems to occur around most stars, producing a large diversity of objects and systems. There are large gaps in our observational record, and numerical methods are not powerful enough to fill in all of these gaps. But progress is being made, and I think that we will only make progress if we work together as a community, both experimentalists, numericists, theorists, and observationalists. To interpret the observations is difficult and often non-unique. So there can be lots of ways that us theorists would be able to explain what you observationalists see. And we need to work very carefully to understand what's actually going on. In addition, often the presence of massive objects has to be inferred. These are non-direct observations. Collisions are a very important fundamental process in planet formation, and we can't forget about them. And if we really think that there are underlying Jupiter-mass planets in some of these transitional disks at tens of AU, there has to be an underlying planetesimal population too. And that planetesimal population is collisionally active. And we cannot ignore the dust that would be produced from those collisions. That's it. Thank you very much.
Thanks very much, Zoe. There's time for questions if anyone wants to ask about that new technique, for example.
Yes, Jay.
Jeffrey, University of Cambridge. I'm wondering what range or type of collisions, or are there a type and range of collisions where a significant amount of molten material is generated throughout the target body? How often? What situations, if at all?
Okay, so that's a really good question. So let me just rephrase and make sure I understand. So you're asking, is there a range or particular set of parameters for collisions that would produce melts? And the melts would have to be in droplet form, or it doesn't matter?
I'm just wondering to get the object, more than 50% or 30% molten.
Well, sure. So if you're totally open for any impacts, then if you hit something hard and fast with something that's roughly the same size, and that thing is large, so that its escape speed is above, so you're hitting it above the sound speed of the material, many times above the sound speed of the material, and it's equal-sized impact, then you can do all sorts of damage to it. If you hit something with something small, but it's going very quickly, then you will generate melts, but it will be very localized. But it would, in that situation, you may actually produce more observable debris because you would have ejecta moving at very high velocity.
Question down the front.
Many super Earths have large, diverse densities.
Yes.
Some of them are very low.
Yes.
And their mass are not that big. And
Yes.
some of them are very high and their mass are very low, and,
Yes.
and so on and so forth.
Right.
Is there any way that from the collision theories that you can come up with not only the average but the range of dispersion for those type of properties?
Right. That's a really Excellent question. I wouldn't have expected anything less from Doug Lin. So, okay. So the question is there a way from impacts that you would be able to explain the diversity and the dispersion that you see even in one system, right? Yeah. I think so, but it still isn't trivial. So certainly you can have a few objects. You could have a system, a planet that was hit, and then another planet in that system that wasn't. Or you could also have something where you had a projectile hit a target, that nothing happens to the target, it's a hit and run event, but the projectile is stripped. And then you would end up with one object that's large that actually might have a lower bulk density, and one object that may end up inside, in semi-major axis closer to the star, that has a much higher density, but is actually lower mass. So I think in addition to just what happens to the solid material, what we haven't been modeling is what happens to the atmospheres and the volatiles during these giant impacts. And I think for the super Earths, that's really important. Because I think that you can have massive vaporization on an object that is very volatile rich. And that could really change the bulk density as well without having to necessarily strip it in the same way. Does that answer your question? Kind of. Okay.
So I have a question. I presume most of the simulations are SPH simulations, right?
Some of them. Okay, your question. Go ahead.
So yeah, my question is, SPH has been used widely, first in cosmology, then it has been applied for many, planetary applications and so on. Recently, cosmologists have been finding problems with SPH by using codes like AREPO, moving grid and so on. Mm-hmm. So would you expect any big differences to occur in your calculations if you would switch to these moving grid schemes, for example?
Okay, so the question is, did I use smooth particle hydrocode in these impacts? A few of them have smoothed particle hydrocode. Most of them are using, instead of Lagrangian, Eulerian grid codes for the shock propagation. So we're using CTH, which is an export-controlled code, and it's a Eulerian grid code. So it doesn't have nearly the same problems that SPH does, but it's much harder to run it for long periods of time, and it doesn't do gravitational reaccumulation. Then we also used an n-body code for the low velocity. So the SPH codes are, the SPH results are moderated by having others. In addition, I think that we have other errors in these simulations that are mostly due to the equation of state. And I think that would probably swamp anything else. So I don't think that we will have any changes in our results because we have larger error from other aspects. Also, it doesn't matter so much what we don't have a big disk where we end up with single particles or a big density change, like a gap or something like that.
Zoe, it's me.
Hello, Rosemary.
My question is related to all those last questions. I was going to ask about equation of state. For example, if you have a melt, how do you actually deal with changing equations of state, and how do you select them? How do you move from one to the other?
Okay. So the equations of state used in all of the shock simulations are tabular equations of state. Some of them are based on anios, and some of them are more accurate than that. The water equation of state is modified by laboratory experiments that my colleague did in her impact laboratory in the basement of Harvard. All of the codes are chosen, well, the grid code is chosen so that because it handles changes in phase very well.
Okay. All right, I'm afraid that's all the time we've got, so if you can join me in thanking Zoe again.